Okay, for our second lesson on dot products, I'm going to go through some specific examples, and I'm also going to show you how to take the dot product of vectors when you're given the component form of the vectors. So let's get started here. So if you're given the vector A is 3x and the vector B is 5y, and we want to take the dot product, we do what we always do. We draw them from a common origin. We become dot product taking machines. Magnitude of the first, magnitude of the second, cosine of the angle between the two. But this is really important. We get cosine of 90 degrees, which is 0. And when we think about the example we used with our energy example, that made perfect sense because those perpendicular forces to the direction of the displacement does not contribute to the energy given to the object. So in our example, remember we had the force, and if A was the delta x vector, that force will not contribute to the motion of the object in the x direction, so it transfers no energy. So this fits very nicely into our energy analysis that we're going to do later in the course. But let me erase that for now. All right, so the first property for dot products is that whenever two vectors are perpendicular, and the fancy math word for perpendicular is orthogonal. Orthogonal means 90 degrees. So anytime vectors are orthogonal, dotting them together gives 0. Nothing. So the answer is always 0. So there's really no calculation to make. As soon as you see you have vectors that are on different axes, you will be getting 0 for that dot product. So again, let me erase this and clean this up a little bit. All right. How about if the vectors are on axis? If the vectors are on axis, there's only one of two possibilities. They're on axis pointing in the same direction, or they're on axis pointing in opposite directions. So let's take a look at that. If we have vector A pointing to the left, backwards on the x-axis, and we have vector B pointing forward on the x-axis, we take dot products the way we take dot products. We are machines. We draw them from a common origin. We take magnitude of the first, magnitude of the second, cosine of the angle between the two, in this case 180, negative 10. So when we have vectors that point in opposite directions, we will always just get the multiplication of the two numbers, and it will be negative. If the vectors point in the same direction, so either they both point forward or they both point backwards, then we will get positive AB, because whether they both point forward or both point backwards, you get cosine of 0 is the angle between them. So, two properties for vectors. If they are perpendicular or orthogonal, you get 0. If they are parallel, you get plus AB. If they are anti-parallel, and yes, anti-parallel is a real thing, that's a word, check with your math teachers, means that you have vectors pointing in opposite directions, you will get negative AB. And that's going to help us out in terms of taking some quick calculations later on. Basically, the next page of notes, we're going to look at that real quick. All right, little table I have here then shows what happens when we have unit vectors. That's why I have the ones here. These are unit vectors. And we're just looking at dotting unit vectors, and if they're on the same axis pointing in the same direction, you get plus 1, 90 degrees orthogonal, 90 degrees orthogonal, 90 degrees orthogonal, 90 degrees orthogonal, orthogonal, orthogonal. So you're only left with like components contributing to a dot product answer. So anytime vectors are off axis from each other, if the vectors are given on axis, you only have to worry about the ones that are parallel or anti-parallel. Okay, let me erase this up. All right then, so let's take a look at dot products in component form. Dot products in component form, I think the best way to look at it is not through just a mathematical explanation as we have here, but to put in actual numbers and make it an example. So if we have vector A, let's say you're given it in component form and in 3 dimensions. So you go over 3 on the x-axis, down 2 on the y-axis, and in this case, positive z would be 4 out of the paper on the z-axis. Boy, that's tough to visualize because that's in 3 dimensions, xy in the plane of the page, and then positive z coming out of the page. But we don't actually have to draw them to make our calculation. So the vector b is 3x, 3y, negative 2z. Again, pretty hard to visualize because that's x and y in the plane of the page and then negative z going into the page. If you tried to take the dot product the way we've done so far, that would be really difficult. You have to draw the vector a and have part of it coming out of the paper. You have to draw the vector b. You have to translate them from a common origin. And what's worse is, how the heck do you calculate the angle between them? That's really messy. We're not going to do it that way. We leave them in component form, and dot product distributes. So if we take vector A and dot it with vector B, we can distribute through. So we take 3x hat dot 3x hat. We take 3x hat dot 3y hat, 3x hat dot 3z hat, and notice we lose the orthogonals. So the x's with the y and with the z give 0 because you have cosine of 90 degrees. So all of those 90 degrees, we would just keep distributing through, right? We would just keep distributing through like we do when we normally multiply, but we're not multiplying, we're dot producting, and we lose all the orthogonals. So we lose the orthogonals, lose those. So what we are left with is only on axis, and they have to either be parallel or anti-parallel. Anti-parallel is going to give us negatives, parallel gives us positives. So I could have just known the parallels give us positive, anti-parallels give us negative, to do 3 times 3 is 9, negative 2 times 3 is negative 6, and 4 times negative 2 is negative 8, and kind of done like a shortcut little cheating way to calculate my answer because I don't really have to go to the cosines. I can just leave the negative and the positive. I can leave that negative and that positive on the y, carry the negative through for me. At any rate, when we take our dot product, look, we get negative 5 for our answer. So I don't have to draw them from a common origin. I just take my like components and take the dot product of the like components to get my answer. Well, this is actually a really powerful technique that we now have to use to calculate the angle between those two vectors. Remember we said if we tried to draw them in 3 dimensions and calculate the angle, how messy that would be? Well, what is really important for you to know, and whether you know it or not, the Pythagorean theorem extends to 3 dimensions. So this is the Pythagorean theorem. Extends to 3 dimensions. So I can get the length of vector A and the length of vector B simply by taking the square root of x squared plus y squared plus z squared square root, and look, I get the magnitude of vector A, I get the magnitude of vector B. Well, dot product is dot product. So I got the answer for my dot product by doing my component form, but A dot B still equals AB cosine theta. I now know A and B because Pythagorean theorem extends to 3 dimensions, so that only leaves me with cosine theta, and I have one equation, one unknown. I can solve that equation. So when you solve for cosine theta, you will have to take cosine inverse to get the angle theta, so practice that on your calculator to make sure you can get the 101.4 degrees is the angle between the two, but pretty cool. So dot product has some very good uses both in math and physics, and we're going to use it much more later on in the course. But for this unit, you absolutely need to be able to take dot products and get correct answers, calculate the angles between 3-dimensional vectors using dot product, and just basically be dot product machines. So that is all for dot products.